Alright, in this lecture we're going to take a deep dive at the notion of measurement error, and we're going to do so by introducing something known as classical test theory. So classical test theory is a very powerful framework used all across social sciences to denote the way that we think about the measurements that we collect. So classical test theory is going to be captured by this simple equation that we have here on screen. It has three main components. X is going to be the observed score, the observed data measurement that I collect when I try to measure some quality of an object. And what classical test theory tells us is that this observed score is going to be a reflection of the linear combination of the true score, the true actual value that of that quality that we're trying to measure, plus or minus some error term. So E here is going to be our error term. So what does this mean? Well, let's think about it in terms of an example. Let's think of a single person that's taking 6 parallel forms of a test. And here, parallel forms is a technical term that I cannot avoid. It's a technical term that we use to refer to interchangeable versions of the same test or measurement instrument. We say that they're interchangeable because we assume they all have the same difficulty and reliability, and because, of course, they are all designed to measure the same construct, to evaluate the same skill, the same knowledge. So let's think about the single person that is taking perhaps 6 different parallel forms of a test. Let's say that these parallel forms are different versions of a midterm that result from sampling different sets of questions from a larger item bank. So what classical test theory tells us is that on each of those 6 different versions of the exam, which we're going to be denoting with this J index, so J is now going to be moving between 1 and 6 to denote a specific value observed. So what classical test theory is that the specific observed value that we find across each of my 6 applications of the test, or my 6 versions of the test, these observed scores that I have here in this table here are going to be a reflection of both the true actual score that the participant deserves, so the true actual score that captures their level of knowledge on this particular thing that we're testing them for. So we have here their true score, which crucially we note it's constant because, again, we presume this is a property of the individual. This is the true value that we're trying to measure. But we still see some variability, or expect to find some variability in the observed scores, because for each of these applications I'm going to have some form of error term. So that's what is captured here by the E letter. So on some occasions I'm going to underestimate the actual true score of the participant here on this first row. And on some occasions I might even overestimate it, right? So again, this error term just captures this idea that there is variability across my measurements. So let's talk a little bit more about this error term. So classical test theory presents us with some key assumptions. The first one is that the error term is random, and as such we say that it is independent of the true score that the participant has. So here we have this little symbol, which is a no notation to denote independence. This just says this value here is independent from this value here. So in other words, the error term is totally random. It cannot be predicted by any other quality of our participants or our measurement instrument even. To simplify things, we're going to model the error term as following a normal distribution. So we're going to assume that the error that we observe on each individual measurement collection, it's going to be a sample from a normal with a mean of 0, so centered at 0, that's going to be the highest value of our distribution, and some unknown variance. And because this normal distribution is centered at 0, we're going to say that the expected value of this error term is going to be 0. This just simply denotes the idea that by using this as our mean value, we are saying that sometimes we expect to overestimate the true score, sometimes we expect to underestimate it, but on average, we expect to have an error term that cancels out to 0. And by imposing this probability distribution on the error term, we are also saying that the observed scores are also going to be behaving as random variables that also follow a normal distribution. Why is that? Well, let's break it up into single steps. If each participant has their own fixed true score, and this fixed true score doesn't change across my measurements, and then the error term adds some random variation that follows this normal distribution to the true score, well, then the observed score is going to be a combination of this true score and this extraction from a normal distribution. We're going to end up with the following implied distribution for the observed scores that tells us that now the observed score that I have on each particular collection of my measurement, it's going to be modeled as following a normal distribution centered at the true score and with some variability or some variance term here that it's going to be inherited from the error distribution, right? So we have here the same variance as the variance used to model the errors. For the visual learners out there, here we have a nice little representation of how this works. So here the red dotted line denotes the true score for my participants. So this is the actual true grade that corresponds to their actual level of knowledge that this test is trying to measure. And the idea is that on each particular parallel form of the test that they are taking, we are observing some error that it's taken from this distribution right here, centered at 0, with some variance. So we extract some error term, and that is going to cause that sometimes the values that I observe end up overestimating a little bit or underestimating the true value that we have here. And the idea is that my observed scores also follow a normal distribution. Again, because the only thing I'm doing is I'm taking this true score as my starting point, and I'm just moving on each observation based on my error term, which is normally distributed. So there is a quick little technical note that I have to specify here, and it's going to be relevant for us to understand the remaining of this lecture. So we have to talk about expected values. So what are expected values? The expected value of any variable that shows random variation is going to be the long run average outcome that we expect this variable to have if we were to repeat the random process many times. In other words, if I were to keep sampling observations from this error distribution here, and I collect many of them, what would be the expected average? So you guessed it, in the case of any variable that follows a normal distribution, the expected value is always going to correspond to the mean parameter of that normal distribution. And intuitively that makes sense, right? If I keep sampling observations from this normal distribution here, sometimes I'm going to overestimate, sometimes I'm going to underestimate, but if I average all my extractions, I expect them to cancel out and to return this same mean value that we have here. Alright, so what does that mean for our classical test theory framework? So for a single person taking the J form of a test, the expected value of the true score that that person is going to have, it's going to be fixed. Why is that? Because again, we said the true score is constant. We assume it's a property of the entity we're trying to measure, in this case the participant taking many parallel forms of a test. The expected value of the error, because the error follows a normal distribution centered at 0, the expected value of the error is going to be 0. So on the long run, over many different parallel forms of a test, I expect all errors to cancel out. And as such, the expected value of the observed scores over many different parallel forms, are expected to converge to the true score of that participant. So that's the idea that we have here. Over many different parallel forms, if we keep collecting observations here, if we keep collecting scores, the average of all those scores that we collect is expected to be the true score. Is expected to correspond to the true score, which is the mean of this distribution for the observed scores. Now let's talk about the variance decomposition, the implied variance decomposition presented by classical test theory. So we said classical test theory tells us that the observed scores that we find on any given measurement are simply a combination of the true score and some error terms, some random variation that occurred during that measurement collection. So that is going to result in a variance decomposition where the variance of the observed scores is also going to be reflected by the sum of the individual variances of the true scores and the error term. So what is the variance of the true scores? Well, this is a variance of 0 because participants' true scores are constant. They don't change across repetitions or across parallel forms. We said that the variance of the error term, we said that we used a normal centered at 0 with some variance here. The total variance that we have here for the observed scores by adding together these two components is also going to end up being the variance of the error term, because it's just going to be 0 plus this variance right here. So this is just saying that the variability across the different measurements that we collect for a single participant with a fixed true score, we expect that to have a variance equal to the variability of the error terms. Now here we have a full decomposition. This is just a summary. For a single person taking parallel forms of a test, single person, just one true score, taking many forms, each of those forms are going to show some variation. As such, we can express the expected value of the observed scores as the sum of the expected values individually for the true scores and the error term. So this is going to be t plus 0, just t. This is our expected value. And the variance is also going to be the sum of their individual variances, and this is going to result in the variance of the error. This is just a summary slide. Now, here we have to introduce the notion of measurement error, because measurement error precisely refers to the difference between the observed score and the true score. Measurement error, it's in the name, denotes the error in our measurement. And importantly, measurement error, even if we try to mitigate it by trying to design the best measurement instrument we can, by trying to ensure the validity of our instrument, by trying to ensure best practices in how we write our items, for example, we always assume that there's going to be some kind of measurement error. Especially in social sciences, no matter how hard we try, we cannot ever assume that the measurements we collect are a one-to-one with the true score that we wanted to measure. And this is also true across other sciences. So for example, even if you take a blood exam where there's a lot of precision in the measurements that they return, we usually expect them to be a little off across different trials by a small amount. We don't expect to have the exact same reading every time we get it. There's always some level of variation that captures this measurement error. And here we have some other examples. However, we do try to control as best as we can for this measurement error, because otherwise this compromises the reliability of our instrument. And we'll talk about this more in a second. Okay, so now we have an important segue. So far, in order to illustrate the idea behind classical test theory, we have talked about a single person with a constant true score, so just one person, and we have used that as an example to talk about the variability in the observed scores across parallel forms of an instrument. So the question is, how does measurement error, so the variability in the measurement that I collect, affects the repeated observed scores I collect for one individual with a fixed true score? Now we're going to think about what happens when we instead look at a more realistic setting in which we are looking at the observed scores across many participants. So now we are introducing a new index notation here. So now we have I for participant, and we're going to keep J for parallel forms. And now what we're introducing pretty much is variability in the true scores across participants. What does it mean? That it is still true that at the level of a single person, the true score is assumed to be constant. It's assumed to be a property of the individual. But when I start considering multiple people, of course I expect to find variability in their individual true scores. So for each particular person, I'm going to assume that they have a unique fixed true score that is going to be sampled from a hidden normal distribution with some mean. We don't know what the mean is, but it has some mean and some variance. And now we have introduced a new source of variability, a new source of variation to the data we can observe. This variation is going to capture the true score variability across my participants. So let's now think about what does it look like using a similar table as what we had before. So each participant, notice here that we have added a new column to denote the new index. Each participant, we have here 3 participants, participant 1, participant 2, and participant 3. Each participant has their own true score, and their true scores are fixed across parallel forms. So this participant has this true score, it's fixed, it's what captures participant 1 skill. Participant number 2 has a different true score. Participant number 3 has a different true score. Now, if we just look at these 3 participants taking 3 parallel forms each, so we have a total of 9 observations, we are now going to see that there's still going to be variability across all of these observed scores, right? So across all 9 scores that I collected across my 3 participants taking 3 parallel forms of a test. But now, the variability in this set of observed scores is going to be a reflection of both the variability in the true score differences across my participants and the variability caused by the random error that just occurs across each observation. So we're now going to have 2 separate sources of variability. We still have our measurement error that it's independent, we said, to the true score, so it doesn't take into account this, it's not predictable, it's just measurement error. But we're also going to have variability in terms of the individual differences across my participants. This variability that we have here, we're going to refer to as a systematic variation. Why is that? Because it is constant at the participant level. Participant 3 always has the highest scores, because he is, or they, he, she, are the ones that have the highest true score across my 3 samples. And this participant that we have here, participant 2, they have the lowest true score. And that is also reflected on the observed scores that we have for them. So there is now a source of systematic variation that is going to be individual dependent. And there's still going to be this unsystematic error denoted by our error term E, which is just random. It's just measurement error. It doesn't depend on the participant. It just occurs and leads us to either overestimate or underestimate our participant scores across measurements. So across participants, true scores vary systematically, and each observation adds unsystematic error. And we keep here our same assumption as before, the error term, because it's totally random, it's totally independent from the true score. Each error term is going to be modeled as a sample from a normal centered at 0 with some variance. Now, the variability across all the observed scores I have collected, it's going to be a reflection of the individual variance of the true scores, so the true score variance, and the variance or the variability in the error term, so the error variance. So now the variability of the observed score reflects both systematic differences between people and random fluctuations that occur within people. So just to be super clear that we have this distinction clear, we started this lecture by talking about the case of just one participant. We have just one index here. T is fixed because we're talking just about one person with their own true score that doesn't change. And we said that we model the observations or the measurements we collect across parallel forms as a combination of that fixed true score and some error. The true score is constant. The error is modeled using a normal distribution. And in this particular case, the only source of variability was the variability in the error terms, was just the measurement error. But when we start considering more participants and we now add this variability across the participants' true scores, because each participant is going to have their own true score, we are now adding a new component to the variability of the observed scores. So now the variability of the observed scores is going to be a combination of the variability in the true scores across participants and or already known variability in the error term. And again, this is heavily linked to the same distinction we first reviewed on lecture 4, but we are now thinking about it in terms of measurement. This is linked to a distinction between unsystematic and systematic variability. So we talked about measurement error as a form of unsystematic variation that just refers to or captures random variation that occurs trial to trial. It's unpredictable, it's not related to anything, it doesn't depend on how good, how bad the participant might be at the task, it just occurs. And then we're going to have some systematic source of variation that we have here, that it's going to capture between persons differences, and that's why we call it systematic. Because even if we expect to find some variability in the scores that the best participant takes across many different parallel forms, we still expect them to perform, because they're the best, we still expect them to get higher scores than the rest of my participants. So this is going to be the systematic variation when I look at between person comparisons. This measurement error averages to 0, again, because we're using a normal distribution centered at 0. And it just captures this idea that we don't really have a reason to expect that the measurement is going to be biased in any direction. Sometimes we're going to overestimate it. Sometimes we're going to underestimate the true score. On average, we expect it to cancel out. But the true score difference here does not necessarily average to 0. Now, measurement error, it's going to be mostly a threat to reliability. Remember that reliability has to do with the consistency with which we observe similar scores whenever we apply the same measurement instrument to measure the same participant over either many occasions or across many raters or people that apply the measurement instrument. So if there's a lot of measurement error, then the reliability is immediately compromised. On the other hand, these true score differences, when they are not related to meaningful between-person differences, they threat the validity of our measurement, meaning that we are not longer going to be able to attribute these differences in the observed scores to the actual variable or the actual quality that we intended to measure. But instead, it might be that they reflect some other property across which my participants vary. Examples that we might have here, so measurement error can be exemplified by any kind of external factor. So sometimes it might be that you take the midterm and you're sitting next to a person that is coughing the entire exam and that breaks your concentration. It can also be attributed to internal factors. It might be that one day you might have had a nightmare, you didn't sleep very well, you're not feeling all that well. So there are a lot of external and internal factors that might cause this random variations or that might help explain these random variations. And when we talk about differences or systematic differences, some of them are meaningful. So some participants might have meaningful differences in ability or skill that make them better at the task, make them more likely to get higher scores or lower scores if it's the opposite. It might also reflect differences in how much participants studies, but it becomes a problem when it's not something related to what we want to study. Say, for example, that some participants had already taken the exam before. So let's say that some participants are retaking the class or something, and they are already familiar with the types of questions asked. They already remember what the questions were. They came in with more information. So they do show some systematic variation. They tend to perform better than the others. So that is inducing some systematic variation that threatens the validity of the assessment. We are not assessing their understanding of the class, we are assessing their memory of the questions. Other examples of unwanted systematic variation might be culturally loaded items or, again, fixed order effects. So here we have some more examples. I'm going to just show them here real quick. You can study them on your own. So far, I would like to take a moment to quickly address, so when is this a problem? So how do we know when this type of variability are a problem? And well, in the case of random error or measurement error, it becomes problematic when the error is too large. In other words, if the variance there is too big, then we're not going to be able to obtain consistent or reliable measurements. It's going to immediately lower our reliability, and as a reminder, reliability is a prerequisite for validity. So if we don't have reliability, we're immediately not positioned to talk about validity. Now, when we talk about systematic variance, when does it become a problem? It pretty much becomes a problem when it is not related to the construct that we want to measure. And when it introduces unwanted bias in the scores. So it's going to threaten the validity of our measurement because we're not going to be able to attribute these differences to the thing we wanted to measure, but to some other thing instead. And how can we reduce this random error? How can we prevent it from threatening our reliability? Well, a very classical or common way of doing it is by increasing the test length. And by that I mean increasing the number of items or questions that we have in our test. And the general idea here is that we are now going to be better positioned to use the average of the observed response that we have across items as a reflection or a closer reflection to the actual true score of that person. So you can think about it in a very practical way. If I want to evaluate how much you have learned about the content that we have seen in this class over the past 5 weeks, I'm going to be much more secure in the estimate that I get if I present to you 10 questions than I would be if I just ask 2 questions, right? So increasing the test length helps us collect more observations and ultimately approximate this observed score distribution that we had on earlier slides. Other approaches include applying the test on multiple times, so that's what I mean by trials here, collecting many observations and then averaging across them to cancel out the noise, try to get a closer estimate to the true value. Other ways, of course, ensuring that the consistency in the instructions and the measurement environment are as standardized as possible so that we prevent this external sources of distraction to induce this measurement error variation. And also by training graders and use super clear rubrics that guide people in grading these evaluations. And how do we reduce systematic error? So first we're going to calibrate our measurement devices and instruments by trying them out on samples that most closely resemble the population that we want to study. Other tools or other common strategies also involve randomizing the order of items and try to counterbalance conditions such that we can prevent confounding effects. So what we mean by this is trying to avoid, for example, having the easiest questions always at the beginning of the exam and then adding difficulty as we keep moving forward. We try to randomize items here. And also by trying to use neutral wording and trying to use leading or culturally loaded content. Try to use not super obscure words or words that are not going to cause extra confusion, avoiding negatives or double negatives. Just trying to ensure that the measurement that we collect is as best as we can ensure it, it's a reflection of the construct we wanted to measure and not something else. And this brings us back on the figure that we have here on screen, illustrating the difference between reliability and validity. So just as a reminder, reliability, which is connected to measurement error, has to do with the degree to which we observe consistent responses or consistent values every time I use the same measurement instrument to measure the same quality in the same object. And validity, which is concerned with this systematic sources of error, is going to be concerned with whether the measurements that I collect are actually targeting that construct that I was interested in measuring in the first place. And this distinction between systematic and unsystematic variance leads us to talk about these two concepts that are also very crucially and centrally related. These are the concepts of signal and noise. Signal is going to be the variability in the observed scores that is related to that construct that we wanted to measure. And the noise is going to be the variability in the observed scores that is just related to, as the name suggests, random variation, just noise. So the observed variance has two components. We said this earlier. It's going to be a combination of the variability in the true scores across participants and the variability on or due to the random error that occurs on each particular iteration of my measurement collection. In this case, my variance of the true scores is going to capture the true variance, the systematic differences across my individuals. And the variance of the error term, the error variance, is going to just capture these random fluctuations. So these two are going to be mapped to this idea of signal versus noise. And again, what this equation is telling us is that the total variance that we observe in all of the observed scores that we collect is going to be a reflection of the variability in the true scores that my participants have and the error variance that just occurs due to measurement error. And this provides a very useful framework to think about reliability. So in the context of classical test theory, reliability is going to be defined as a ratio of the variance in the true scores to the variance in the observed scores that we have. In other words, it's going to be a matter of how much of the variability that I find across all my observed scores, how much of that is attributable or can I attribute to the differences or the variability in my true scores. So it's going to be a ratio between this true variance and the sum of the true variance and the error variance, which together form or describe the variability of the observed scores. So in this framework, reliability has a very nice interpretation. It just tells us the proportion of the observed variance that reflects actual true differences between people instead than just random error. Because it's a ratio, this notion or this definition of reliability only allows for values that fall within the range 0 to 1. So 0 would denote a case in which all variance is noise, so there's no variance here attributable to the between people differences, so this is 0, and then the whole thing turns to 0. All variance is noise, all variance comes from the error term. And the opposite value would be, or on the opposite end, we have values of 1, in which all the variance is assumed to reflect true scores, a perfect measurement. Well, all our variability is due to variability across individuals. In practice, higher reliability indicates more consistent, dependent measurements, but of course, we never actually expect this value to get to 1. And in fact, we are going to be a little limited on how we can accommodate this because precisely we cannot observe the true scores. But we will talk more about this on a future lecture. Alrighty, so here is the question for you. In this question for you, you just have to read through each of these 6 scenarios and decide whether the type of variability described here captures an example of systematic or random variability.